Hello everyone! In this video we will continue to examine topic 12.1, the interaction of matter with radiation, and in particular we will continue to discuss the uncertainty principle. Alright, so question, what if you measure the position? So this is just a free particle, and we said that the product of the uncertainty in the position and the uncertainty in the momentum had a lower bound, h over 2 pi. H over 4 pi. That is, this product must be at least this big. And we've got a question. What if you measure the position? What happens? Okay, well, we've discussed this before, but if you measure the wavelength directly, you will find, measure the position of the particle directly, you will find that particle in a particular point. And then with approximately 100% certainty, we'll find it at that point again. And you get in that process what we've called wave function collapse. So the wave function collapses to what is known as a Dirac delta function right around that area, that is basically a spike in the wave function itself. And note that if the wave function looks like a spike, there's a very, very small uncertainty in the position, right? A little tiny delta x corresponding to the width of the spike. But if you take a look at it, it is very evident that there is no obvious wavelength at all. And in fact, the momentum, as a result, is completely uncertain because the wavelength is completely uncertain. And that reflects that if delta x is really small, okay, delta p will need to be at least a certain magnitude in order for the product to be larger than or equal to h over 4 pi, okay? All right, so let's follow up here. Well, what happens if you measure its velocity or its momentum? Take a moment to consider what you think might happen to the wave function. And let's take a look. Well, if you measure its position, its momentum or velocity, okay, what you get is a wave function that has a perfectly well-defined wavelength. That is, you get a sinusoidal wave function. Okay. Now, a sinusoidal wave function, just like a Dirac delta function, that is this spike here, doesn't quite obey the normalization that is necessary. That is, if it were exactly a sine wave, then the sum of the probability under the curve of psi squared would not be equal to 1, but remember, this is the hypothetical case where that momentum is measured, and so it will look more sine wave-like. Just like this in practice will look more spiky, but not perfectly spiky. This will look more sinusoidal, but not perfectly sinusoidal in practice. And in either case, if this is the wave function that you get when you measure its momentum, and it has a very precise wavelength, that will give you a very large uncertainty in the position, okay? A very large uncertainty in the position. And so these things are sort of trade-offs. The more precisely the position exists, I don't want to say is known, I want to say exists, the more definite to within that bound it exists, then the less definite the momentum is, and vice versa. Make sure you take a look at this example problem here.